The Gulf of Mexico is heating up to levels that are drawing serious attention from scientists. Beneath the surface, enormous amounts of thermal energy are building through layers of unusually warm water, creating conditions that can provide powerful fuel for tropical storms. But warm water alone does not guarantee a major hurricane. Wind, moisture, ocean depth, and atmospheric conditions must all align. In this documentary, the science behind the Gulf's record-breaking heat reveals what it could mean as hurricane season unfolds. If calm, detailed science documentaries are worth exploring, please like the video, subscribe to the channel, and join the journey into the forces shaping our planet. The Gulf of Mexico occupies a warm basin between North America, the Caribbean, and the Western Atlantic Ocean. Its shape, latitude, and circulation allow it to collect and retain large amounts of solar energy through much of the year. Sunlight reaches the water while warm air often lies above the sea for long periods. These conditions make the Gulf naturally warm, especially from late spring through summer, but the background climate in which this seasonal warming occurs is changing. Earth's climate system is gaining heat because concentrations of greenhouse gases in the atmosphere are higher than they were before large-scale industrialization. Carbon dioxide, methane, and other heat-trapping gases slow the loss of infrared energy to space. The resulting imbalance is small compared with the total energy moving through the climate system each day, but it persists continuously. Over decades, that persistent imbalance adds an enormous amount of heat to the planet. Most of this additional heat does not remain in the atmosphere. The global ocean absorbs the great majority of the excess energy associated with human-caused warming. Water has a high heat capacity, meaning it can store large quantities of energy while warming relatively slowly. This property moderates atmospheric temperature change, but it also means that ocean warming can continue beneath the surface and remain present for long periods. The Gulf of Mexico shares in this wider ocean warming. Its temperatures still vary from year to year and from season to season. Winds, clouds, rainfall, ocean currents, river discharge, and exchanges with the Caribbean and Atlantic all influence its thermal state. Natural climate patterns can temporarily raise or lower temperatures over parts of the basin. These variations remain important, but they now operate on top of a warmer, long-term background. Observations across the world's oceans show a clear rise in average ocean temperature and ocean heat content over recent decades. The upper layers warm most visibly because they interact directly with sunlight and the atmosphere, while deeper layers also store part of the added energy. In a semi-enclosed sea such as the Gulf, regional circulation can concentrate or redistribute this heat in ways that differ from the open ocean. The Gulf is also influenced by the warm waters that arrive from the Caribbean. These waters enter through the Yucatan Channel curve through the basin and later leave through the Florida Straits. The circulation is not fixed, it shifts, bends, and releases large rotating bodies of water. These movements help determine where warm water gathers and how long it remains in particular areas. Seasonal heating adds another layer of change. As the sun climbs higher in the sky during spring and summer, the Gulf receives stronger solar energy. Days become longer and the upper ocean usually warms. Calm conditions can allow the surface to heat more rapidly because less wind-driven mixing carries that warmth downward. Cloud cover can reduce incoming sunlight, while stronger winds can increase evaporation and stir cooler water upward. The balance among these processes changes from day to day. A warmer climate does not remove this natural variability. Instead, it shifts the range within which the variability occurs. A warm season influenced by favorable atmospheric and oceanic conditions can therefore begin from a higher baseline than a similar season did many decades earlier. This makes exceptionally warm conditions more likely and can raise the temperatures reached during marine heat events. The phrase record-breaking heat describes measurements that exceed values observed within a particular data record region, depth, or time of year. Such records require careful interpretation because different observing systems cover different periods and areas. Satellite measurements provide broad views of the ocean's surface, while buoys, ships' floats, and other instruments sample conditions within the water. Together, these observations allow scientists to compare present warmth with past conditions while recognizing the limits of each record. Across the Gulf, the central scientific concern begins with this accumulated heat. The basin is naturally warm, seasonally variable, and strongly connected to surrounding ocean currents, yet it now exists within a climate system holding more energy than in the past. That broader warming does not determine any single season by itself, but it changes the background conditions against which each season develops. Above the Gulf of Mexico, the atmosphere forms the first moving layer that controls how heat enters, leaves, and circulates around the sea. During the warm season, air over the basin is often humid because evaporation transfers water vapor from the ocean surface into the lower atmosphere. This moisture becomes part of a tropical air mass that can extend from the Caribbean across the Gulf and into the southern United States. The temperature of this air changes through the day and from one weather pattern to another. Sunlight warms the ocean and surrounding land while the sea releases stored heat back into the atmosphere. Because water warms and cools more slowly than land, the Gulf often remains warm after land areas begin to lose heat during the evening. This difference helps maintain warm, moist air over the basin through the night. Winds determine how that air moves. Near the surface, winds are shaped by pressure differences across the region, Earth's rotation, and the position of weather systems. Persistent southerly or southeasterly flow can carry humid Gulf air toward the coast. Other patterns can bring drier continental air southward. When winds are weak, the lower atmosphere may remain closely connected to the warm sea beneath it. When winds strengthen, they increase evaporation and can also stir the upper ocean. Clouds alter the balance of energy above the Gulf. Thick cloud cover reflects part of the incoming sunlight back towards space, reducing the amount of solar energy reaching the water. Clouds also absorb and emit infrared radiation, limiting some of the heat that escapes upward from the surface. Their effect depends on cloud height, thickness, time of day, and the amount of sunlight present. Humidity also influences how the surface loses heat. Warm ocean water produces evaporation, especially when the air above it is relatively dry or when winds increase. Evaporation removes energy from the surface because liquid water requires heat to become vapor. When the air is already very humid, the difference between the ocean surface and the atmosphere becomes smaller, and evaporation can become less efficient under otherwise similar conditions. Large-scale pressure systems can keep particular weather patterns in place for days. A region of high atmospheric pressure can suppress cloud formation and reduce rainfall. Under some conditions, it can also weaken winds across part of the basin. Clear skies then allow strong solar heating during the day, while limited wind reduces the mixing that would otherwise spread surface warmth through a deeper layer of water. Rainfall introduces another influence. Heavy rain can temporarily cool the surface through direct contact with cooler drops and through changes in evaporation. Fresh rainwater can also reduce surface salinity. Because fresher water is less dense than saltier water, a thin surface layer can become more stable and resist mixing with water below. The effect varies greatly depending on rainfall amount, wind currents, and existing ocean structure. Dust and aerosols transported through the atmosphere can slightly change how much sunlight reaches the sea. Saharan dust sometimes crosses the tropical Atlantic and Caribbean before reaching the Gulf. These particles scatter and absorb a portion of incoming solar radiation and can influence cloud processes. Their regional effects are measurable, although they are only one part of a larger energy balance. The atmosphere above the Gulf therefore acts neither as a simple blanket nor as an independent system. It exchanges heat, moisture, and momentum with the sea every hour. Calm air, strong winds, clear skies, cloud cover, rainfall, and humidity each alter the rate at which the Gulf gains or loses energy. Scientists observe these conditions with satellites, weather stations, buoys, research aircraft, and numerical weather models. Measurements of air temperature, humidity, pressure, wind clouds, and rainfall help describe the environment above the water. These observations show that extreme ocean warmth develops through a combination of persistent atmospheric conditions and the heat already stored within the Gulf. In this outer atmospheric layer, the important pattern is one of continuous exchange. The sea warms the air modifies the sea, and large weather systems control how quickly those exchanges occur. The resulting balance can either slow seasonal warming or allow heat to accumulate more efficiently across the basin. Sunlight is the main external source of energy warming the surface of the Gulf of Mexico. During late spring and summer, the sun remains high in the sky for long periods, and the basin receives strong solar radiation. Part of that energy is reflected by clouds and haze, but a large fraction enters the upper water and is converted into heat. The amount of sunlight reaching the sea changes with season, latitude, cloud cover, and the angle of the sun. When the sun is higher, its energy is concentrated over a smaller area and passes through a shorter path in the atmosphere. This allows more radiation to reach the water. During summer, long daylight hours increase the total energy available to warm the Gulf. The ocean does not absorb all wavelengths of light in the same way. Infrared radiation is absorbed very close to the surface, while visible light can penetrate farther before its energy is converted into heat. Blue and green wavelengths generally travel deeper than red wavelengths in clear seawater. Suspended particles, plankton, and dissolved material can reduce this penetration and cause more energy to be absorbed nearer the surface. The Gulf contains waters with different levels of clarity. Offshore regions can be relatively clear, while coastal areas receive sediments, nutrients, and organic material from rivers and shallow seafloors. These differences affect how sunlight is distributed through the upper water. Clearer water can allow solar energy to spread through a deeper layer, while more turbid water absorbs a larger share closer to the surface. Clouds provide one of the strongest short-term controls on solar heating. A clear day allows a greater fraction of incoming sunlight to reach the Gulf. Thick clouds reflect much of that radiation back towards space before it can enter the ocean. Thin clouds may reduce sunlight less strongly. Because cloud fields change continually, the amount of solar energy reaching a particular part of the basin can vary from one day to another. The angle of the ocean surface also matters. Waves create moving slopes that reflect and refract light in different directions. Under calm conditions, the surface is smoother, but reflection still depends on the position of the sun. When sunlight strikes the water at a low angle, more energy is reflected. When it arrives more directly from above, a larger fraction can enter the sea directly. Once solar radiation is absorbed, molecular motion increases and the water warms. This heating is strongest in the upper ocean because most sunlight is absorbed before reaching great depth. The surface temperature, therefore, responds quickly to changes in sunlight, especially when winds are light and the upper water is not mixed rapidly. The daily cycle leaves a thermal pattern. Strong sunlight can warm the uppermost layer during the afternoon. At night, incoming solar energy disappears while the sea continues to lose heat through infrared radiation, evaporation, and contact with the air. Under calm conditions, daytime warming can remain concentrated close to the surface. Stronger winds can reduce this difference by stirring heated water downward. Seasonal accumulation occurs because the Gulf receives more energy during the warm months than it loses over many consecutive days. The sea, therefore, stores part of the incoming solar heat. The exact rate varies across the basin, and currents move water from one location to another. Even so, persistent periods of bright skies and weak winds can favor rapid warming of the surface. Scientists estimate incoming and reflected solar radiation using satellites, atmospheric observations, and instruments at the ocean surface. These measurements help determine the surface energy balance, which describes the difference between energy entering and leaving the sea. The balance is never controlled by sunlight alone, but solar radiation supplies the basic energy that drives the seasonal rise in temperature. Across the Gulf, this process is continuous and quiet. Photons arriving from the sun pass through the atmosphere, cross the moving surface, and are absorbed within the water. Their energy becomes part of the ocean's thermal reservoir, changing the temperature of the upper sea by amounts that accumulate across hours and days. During periods when skies remain clear and losses are limited, this steady input can raise surface temperatures above their earlier seasonal state. Sea surface temperature provides one of the clearest ways to observe how much the uppermost layer of the Gulf of Mexico has warmed. It describes the temperature of the ocean skin and the water immediately beneath it, depending on the observing method, because this thin layer exchanges energy directly with the atmosphere. It can respond rapidly to sunlight, wind clouds, evaporation, and passing weather systems. Scientists measure sea surface temperature with several complementary systems. Satellites detect infrared and microwave radiation emitted from the ocean's surface and convert those signals into temperature estimates. Infrared instruments provide detailed views when skies are clear, while microwave observations can sometimes see through clouds more effectively, but at lower spatial resolution. Buoys, ships, and other instruments measure temperature directly in the water and help check the accuracy of satellite observations. Each method samples a slightly different part of the upper ocean. A satellite may sense only the very thin surface skin, while a buoy thermometer usually sits deeper below the waves. During calm, sunny afternoons, the upper few centimeters can become warmer than the water beneath. At night or during windy weather, mixing reduces this difference. Scientists account for these effects when combining observations into larger temperature records. A temperature becomes record-breaking only in relation to a defined record. The comparison may involve a particular location, a daily average, a monthly average, or the entire basin. The length of the observing period also matters. A value can be the highest measured since modern satellite records began without necessarily representing the warmest condition in every earlier century. Careful language keeps the observation tied to the data that actually exist. The seasonal cycle remains important. Gulf surface waters normally warm through spring and reach their highest temperatures during summer. They then cool as sunlight weakens and cold fronts become more frequent later in the year. Scientists therefore compare present conditions not only with annual averages but also with temperatures normally expected for the same time of year. An anomaly is the difference between an observed temperature and a long-term reference average for that place and date. A positive anomaly means the water is warmer than the reference value. When large positive anomalies cover broad areas for many days, they indicate that the unusual warmth is not confined to a single buoy or a small coastal zone. Spatial patterns across the Gulf can be complex. Shallow coastal water may warm rapidly during clear, calm weather because there is less water available to absorb the incoming energy. Offshore regions can behave differently because currents transport heat through the basin and because deeper water changes the response to wind-driven mixing. A basin-wide average, therefore, smooths many local contrasts. Satellite maps allow scientists to see these contrasts across thousands of kilometers of ocean. Warmer patches can form shift merge or weaken as winds and currents change. Coastal observations add detail where satellite measurements may be affected by clouds land contamination or shallow water conditions. Together, the observing systems provide a more complete picture than any single instrument. Record surface warmth does not mean that every part of the Gulf reaches the same temperature. It also does not by itself describe how much heat is stored deeper below. Surface temperature is a boundary measurement useful because it directly reflects the water in contact with the atmosphere. Its importance comes from showing the immediate thermal state of the sea over wide areas. Long-term records reveal that extreme warm values are becoming more common as the global ocean warms. Natural variability still produces warmer and cooler years, and short-term weather can change the surface quickly. Even so, the underlying rise in ocean temperature shifts the range within which those variations occur. For scientists, the central observation is therefore not a single isolated number. It is the persistence, extent, and seasonal timing of unusually warm surface water across the Gulf. These features show how strongly the upper boundary of the ocean departs from its usual state and provide a measurable record of heat accumulating at the surface. Repeated measurements across days and weeks help distinguish brief weather-driven spikes from broader warm conditions that remain established across substantial portions of the basin over time each season. A marine heat wave is a period when ocean temperatures remain unusually high for a particular place and season. Scientists identify these events by comparing present temperatures with a long-term historical range. The definition focuses on persistence as well as intensity, because a single warm afternoon is different from a broad area of ocean remaining warmer than normal for many consecutive days. In the Gulf of Mexico, marine heatwave conditions can develop when several influences act together. Strong sunlight can warm the surface. Weak winds can reduce mixing, and humid air can limit some heat loss through evaporation. At the same time, currents may transport additional warm water into the basin or redistribute existing heat across wide areas. When these conditions persist, unusually high temperatures can become established rather than disappearing after a short weather change. The duration of a marine heat wave matters because living systems and physical processes respond not only to temperature, but also to how long that temperature remains elevated. A brief, warm period may have limited effects, while persistent warmth can expose marine organisms to sustained thermal stress. Coral reefs, seagrass beds, plankton, communities, fish, and other organisms differ greatly in their tolerance, and responses vary with species, location, depth, water quality, and previous conditions. Marine heat waves are usually described relative to local climate rather than by one universal temperature threshold. Water that is unusually warm in the northern Gulf may still be cooler than ordinary summer water farther south. Scientists therefore compare each region with its own seasonal history. This approach makes it possible to identify abnormal warmth across environments that naturally have different average temperatures. The shape of the Gulf allows warm anomalies to form in connected but uneven patterns. Shallow shelves can heat rapidly, while deeper offshore regions respond more slowly. Coastal waters are influenced by rivers, tides, sediment, and local winds. Open water regions are more strongly affected by large currents and rotating eddies. A marine heat wave can therefore cover much of the basin while still containing patches with different temperatures and rates of change. Persistence is also influenced by the atmosphere. Repeated periods of clear skies can continue adding solar energy. Weak winds may keep the warmest water near the surface, while strong winds can mix that heat downward or bring cooler water upward. Passing fronts can interrupt a heat wave, especially in cooler seasons, but during summer, the air itself may be too warm to produce strong surface cooling. Scientists track these events with daily satellite observations combined with measurements from buoys and other ocean instruments. A sequence of temperature maps reveals whether an anomaly is expanding, shrinking, moving, or remaining nearly stationary. Long records allow researchers to compare the duration and intensity of present events with earlier decades. These comparisons show that marine heat waves have become more frequent and more intense in many parts of the global ocean as average temperatures have risen. The Gulf reflects this larger pattern while retaining strong regional variability. Some years contain widespread and persistent warmth, while others are interrupted by storms, strong mixing, cloudier conditions, or changes in circulation. Human-caused climate warming increases the background temperature, but it does not remove the influence of these short-term and regional processes. A marine heat wave, therefore, represents more than a hot surface reading. It describes an ocean state that remains outside its usual seasonal range for a sustained period. The scientific importance lies in the combination of magnitude, area, and duration. A broad anomaly lasting many days indicates that the upper ocean is holding more heat than is typical for that time of year. Within the Gulf, such persistence can create a stable, warm environment over large distances. The water may continue exchanging energy with the atmosphere, yet the accumulated heat is not removed quickly enough to return temperatures to normal. This slow imbalance is what allows a temporary warm spell to become a defined marine heat wave. Repeated warm events can alter the rhythm of the basin. When elevated temperatures begin earlier or persist later than usual, the period of exposure lengthens. Scientists examine these timing changes separately from peak temperature because duration can influence both ocean physics and biological stress, even when the maximum temperature is not exceptional. Beneath the immediate surface of the Gulf of Mexico lies the ocean mixed layer, a region where wind waves and turbulence continually stir the water. Within this layer, temperature and salinity are often relatively uniform compared with the more sharply layered water below. Its thickness changes with weather season, location, and the strength of ocean currents. During periods of strong wind, the surface is disturbed and mechanical energy is transferred downward. Waves break currents, shear against one another, and turbulence carries warm surface water deeper while bringing cooler water upward. This process spreads heat through a larger volume of water. When mixing is vigorous, the sea surface may cool even though the total amount of heat in the upper ocean changes only modestly. When winds weaken, the opposite tendency develops. Sunlight can warm the uppermost water faster than turbulence can distribute that energy downward. A shallow, warm layer may then form near the surface. If calm conditions persist, the temperature difference between the surface and deeper water can increase through the day and remain partly established overnight. The depth of the mixed layer is therefore important for understanding how quickly surface temperature can rise. A thin mixed layer contains less water, so a given amount of solar energy produces a larger temperature increase. A deeper mixed layer spreads the same energy through more water, producing a smaller change at the surface. Seasonal conditions alter this structure. During warmer months, strong solar heating tends to make surface water lighter because warm water is less dense than cold water. This favors a shallower mixed layer in many regions. During cooler periods, surface heat loss can make upper water denser, allowing it to sink and encouraging deeper mixing. Rainfall can also affect the mixed layer. Fresh water delivered by heavy rain is less dense than salty seawater. When it accumulates near the surface, it can form a light layer that resists mixing with the saltier water below. Strong winds can break down this structure, but under calmer conditions it may help keep heat concentrated close to the surface. The mixed layer is not equally deep across the Gulf. Coastal shelves, open water regions, current boundaries, and rotating eddies all have different physical conditions. Local winds can deepen the layer in one area while another remains relatively shallow. Oceanographers, therefore, measure mixed layer depth across many locations rather than treating the basin as uniform. Temperature profiles collected from floats, research vessels, gliders, and other instruments reveal the vertical structure directly. A sensor lowered through the water records how temperature changes with depth. Where the measurements remain nearly constant, the water is well mixed. Where temperature begins to fall more rapidly, the mixed layer approaches its lower boundary. This boundary can move over short periods. A windy day can deepen it, while several calm and sunny days can allow it to become shallower. Because the Gulf experiences frequent weather changes, the mixed layer is a dynamic region rather than a fixed slab of water. Heat stored inside this layer remains available to interact with the atmosphere. The surface can lose energy through evaporation and infrared radiation, while sunlight continues to add energy during the day. Mixing determines how strongly those gains and losses affect the measured surface temperature. Scientists distinguish between surface warmth and the total heat contained within the mixed layer. Two locations can have similar surface temperatures but different amounts of stored energy. If their warm layers have different depths, a shallow warm layer may cool quickly when winds increase, while a much deeper warm layer can resist short periods of surface cooling. The same layer also responds to daily changes in heating. Afternoon sunlight can strengthen a warm surface gradient, while nighttime cooling weakens it. Repeated cycles leave a constantly adjusting boundary whose depth records the recent balance among solar input, wind stirring rainfall, evaporation, and heat loss to the surrounding atmosphere. Across the Gulf, the mixed layer acts as a moving reservoir between the atmosphere above and the deeper ocean below. Its depth changes as energy enters, leaves, and is redistributed. These changes control how visible surface warmth responds to weather and how long accumulated heat can remain present in the upper sea. Below the ocean mixed layer, the Gulf of Mexico often develops stronger differences in temperature and salinity with depth. These differences create stratification, a condition in which lighter water rests above denser water and vertical movement becomes more difficult. Stratification is a normal feature of warm oceans, but its strength changes with season weather, rainfall currents, and the amount of heat stored near the surface. Temperature is one of the main controls on seawater density. Warm water is generally less dense than cooler water, so strong surface heating can create a stable arrangement in which warm water remains above colder water. Salinity also matters. Fresh water is less dense than salty water, and rainfall or river discharge can therefore strengthen the separation between surface water and the layers below. During summer, the Gulf often receives enough solar energy to maintain a warm upper layer for long periods. If winds remain weak, turbulence may not be strong enough to mix this warm water downward. The result is a sharper temperature gradient between the upper ocean and deeper water. Oceanographers often describe the zone of rapid temperature change as the thermocline. A strong thermocline acts as a barrier to vertical mixing. It does not stop movement completely, but it requires more energy for surface turbulence to penetrate into deeper water. Gentle winds may stir only the shallow layer above it. Under these conditions, heat delivered by sunlight can remain concentrated near the surface rather than being distributed through a much greater depth. Salinity can reinforce this stability. Near the northern Gulf, major rivers discharge large amounts of fresh water into coastal regions. Rainfall can add another layer of fresh water across the surface. When warmer and fresher water occupies the top of the ocean, both temperature and salinity differences can reduce its density relative to deeper water. This makes vertical exchange more resistant to ordinary wind stirring. The strength of stratification varies from place to place. Shallow coastal waters respond quickly to local weather and river flow. Offshore regions are influenced more strongly by currents, eddies, and the movement of water entering from the Caribbean. Some locations can remain strongly layered for days, while nearby areas become mixed by stronger winds or changing circulation. Scientists measure this structure by recording temperature and salinity through the water column. Instruments carried by research ships, profiling floats, autonomous gliders, and moored sensors reveal how density changes with depth. These measurements allow researchers to identify where the ocean is well mixed and where stable layers separate warmer surface water from cooler water below. Stratification can change over the course of a single day, but persistent patterns usually reflect a balance among heating, freshwater input wind and currents. Strong daytime heating can increase stability near the surface. Nighttime cooling may weaken it slightly. A period of sustained wind can deepen the mixed layer and reduce temperature differences, while calm weather can allow the layers to form again. This layering has important consequences for how the Gulf stores and releases heat. A strongly stratified surface can warm rapidly because the heat remains confined to a relatively small amount of water. The same structure can reduce the upward movement of cooler water that might otherwise lower the surface temperature. As a result, unusually warm conditions can persist even when deeper water remains distinctly cooler. The density boundary also influences how small disturbances travel through the water. Internal waves can move along layers of different density without immediately destroying them. These motions redistribute energy and occasionally promote mixing, but much of the layered structure can survive. The Gulf, therefore, contains a constantly shifting pattern of stable and less stable regions, each responding to local heating, freshwater currents, and wind with different degrees of resistance. Stratification is therefore not simply a boundary between warm and cold water. It is a changing physical structure that controls the ease with which heat moves vertically through the Gulf. When the upper ocean becomes strongly layered, the connection between the surface and deeper water weakens. The heat gained near the top can remain concentrated there for longer periods, shaped by a quiet balance between buoyancy wind, stirring rainfall, and the slow movement of the sea. The loop current is one of the most important pathways carrying warm water through the Gulf of Mexico. It enters the basin from the Caribbean through the Yucatan Channel, curves northward into the Gulf, then turns east and exits through the Florida Straits. From there, its waters contribute to the Florida Current and eventually to the Gulf Stream system of the western North Atlantic. The current is not a narrow river flowing through a fixed channel. It is a broad, powerful circulation feature whose shape changes over time. At some periods it extends far north into the central Gulf. At other times it remains farther south. These changes alter where the warmest water is located and how deeply that warmth reaches beneath the surface. Water entering from the Caribbean is generally warm and salty. Because the current transports large volumes of this tropical water, it carries substantial thermal energy into the Gulf. The temperature at the surface is only part of this structure. Warm water can extend to considerable depth within the loop current, creating a thick reservoir rather than a shallow skin of heat. As the current grows northward, it can become unstable. Large bends form along its path, and eventually part of the circulation may separate from the main current. The detached feature becomes a warm core eddy, a rotating body of water that can remain inside the Gulf for months. These eddies often move slowly westward while carrying heat across the basin. A warm core eddy rotates clockwise in the northern hemisphere. Its center usually contains water that is warmer and often deeper than the surrounding ocean. The sea surface may rise slightly over the eddy because the warm water expands and creates a thicker column. Satellites can detect the subtle changes in sea surface height, helping scientists follow the movement and evolution of the feature. Eddies do not remain unchanged. They interact with smaller currents. Nearby eddies, winds, and the continental margins, their boundaries can stretch and distort, while fragments of warm or cooler water are exchanged with the surrounding Gulf. Even as their shape changes, some maintain a deep, warm core for long periods. The position of the loop current and its eddies therefore contributes to large differences in heat storage across the Gulf. Two nearby regions can have similar surface temperatures but very different temperature profiles below. Water inside a warm eddy may remain warm through a much greater depth than water outside it. This difference becomes important when scientists assess the total thermal state of the basin. Oceanographers monitor the loop current using satellites, drifting instruments, underwater gliders, floats, moored sensors, and measurements collected from ships. Satellite observations show surface temperature and sea level patterns, while instruments in the water reveal the vertical structure. Combining these observations allows researchers to estimate where deep, warm water is concentrated. The current also changes in ways that are not completely regular. Eddies separate at irregular intervals, and their timing depends on complex ocean dynamics. Scientists understand the broad physical processes involved, but the exact evolution of the loop current cannot be predicted far in advance with complete precision. Continuous observation is therefore important for describing its present state. Seasonal heating still affects the water moving through this circulation. Sunlight warms the surface, winds mix the upper layers, and atmospheric conditions regulate heat loss. Yet the loop current adds another mechanism by transporting heat horizontally from lower latitudes into the basin. It redistributes warmth rather than creating it, carrying stored tropical energy from one region to another. Across the Gulf, this moving circulation creates a shifting map of deep and shallow warmth. The loop current may form a long arc of tropical water, while detached eddies carry portions of that heat away from the main pathway. Each feature moves slowly through a much larger ocean system, continuously exchanging water with its surroundings. The result is a basin whose thermal structure cannot be understood from surface heating alone. Warmth is also carried by organized currents with depth, momentum, and persistence. The loop current is the clearest expression of this process in the Gulf, transporting tropical water through the basin and concentrating large reservoirs of heat along a changing dynamic route. Beneath the warm surface of the Gulf of Mexico, temperature changes gradually with depth. The visible surface may respond quickly to sunlight, wind, clouds, and rainfall, but deeper water changes more slowly. This difference creates an important distinction between surface warmth and the amount of heat stored within the upper ocean. A very warm surface does not always mean that the water beneath it is equally warm. During calm weather, sunlight can heat a relatively thin layer near the top. If stronger winds arrive, that shallow warmth may be mixed downward and the surface temperature can fall rapidly. In another location, warm water may already extend through tens of meters or more. There, the same wind can mix the ocean without bringing much cooler water to the surface. Scientists study this vertical structure by measuring temperature through the water column. Instruments on research ships can be lowered from the surface toward deeper layers. Autonomous floats rise and sink while recording temperature and salinity. Underwater gliders travel slowly through the sea, repeating profiles across large regions. Moored instruments remain fixed in one place and record how conditions change over time. These measurements reveal layers that satellites cannot see directly. Satellite sensors provided excellent coverage of the surface, but they do not measure deep temperature in the same way. A surface map may show two areas with nearly identical temperatures, while subsurface observations reveal that one contains a much thicker layer of warm water. The depth of the warm layer depends on several processes. Currents can transport warm water into the Gulf. Eddies can trap and carry thick bodies of tropical water. Wind can deepen the mixed layer. Repeated periods of heating can gradually increase the temperature of the upper ocean. The resulting pattern varies across the basin and changes continually. Temperature usually decreases beneath the mixed layer as depth increases. The transition can be gradual or relatively sharp. Where a strong thermocline is present, a small change in depth may produce a noticeable decrease in temperature. In other regions, wind and currents can weaken this gradient and create a broader zone of warm water. Warm water at depth has greater persistence than a thin, heated surface. The atmosphere interacts most directly with the upper boundary of the ocean, so surface water can cool during cloudy weather, strong evaporation, or passing storms. Heat stored deeper below is more isolated from these rapid changes. It can remain available even after the surface has cooled temporarily. This makes subsurface measurements important when scientists assess the thermal condition of the Gulf. A single surface temperature describes only the boundary between ocean and air. A vertical profile shows whether that warmth is shallow or extends through a much larger volume of water. The distribution is especially uneven around major currents and warm core eddies. Within these features, warm tropical water can extend considerably deeper than in surrounding regions. Outside them, cooler water may lie closer to the surface. These differences can exist across relatively short horizontal distances. Depth also changes how slowly temperature responds to atmospheric conditions. Near the surface, a strong weather event can produce noticeable changes within hours. At greater depth, changes generally occur more gradually because the water receives less direct solar energy and is less directly exposed to the atmosphere. Currents and mixing become the main ways heat is transported there. Scientists therefore examine complete temperature profiles rather than treating the Gulf as a flat, warm surface. They look at how deep particular temperature levels extend and how those depths change across time and space. Repeated measurements reveal whether deep warmth is expanding, weakening, or being carried into another part of the basin. The difference between shallow and deep warmth is fundamentally a difference in stored energy. A thin layer can reach a high temperature while containing less total heat than a thicker layer that is slightly cooler. The volume of warm water matters alongside the temperature itself. Beneath the surface, the Gulf becomes a three-dimensional reservoir whose heat is distributed through changing layers. Some regions contain warmth only near the top, while others hold it much farther downward. Understanding this hidden structure allows the thermal state of the basin to be described more completely than surface observations alone can provide. Ocean heat content describes the amount of thermal energy stored within a volume of seawater. It depends on both temperature and the depth through which warm water extends. For the Gulf of Mexico, this measure provides a fuller picture of thermal conditions than sea surface temperature alone because it includes the heat held beneath the upper boundary of the ocean. Two areas can have nearly identical surface temperatures while containing very different quantities of stored heat. In one area, warm water may extend only through a shallow layer. In another, similar warmth may continue much farther downward. The second region contains a larger reservoir of thermal energy because a greater mass of water is warm. Scientists estimate ocean heat content from vertical measurements of temperature together with information about seawater density and the depth of the warm layer. Profiles collected by floats, gliders, research vessels' moorings, and other observing systems reveal how temperature changes below the surface. These measurements are combined with satellite information and numerical models to describe conditions over larger areas. The Gulf is particularly important for heat content measurements because its circulation can create deep pockets of warm water. The loop current and warm core eddies often contain tropical water that remains warm well below the immediate surface. In these regions, the upper ocean may hold substantial heat, even when surface temperatures look similar to surrounding waters. Heat content changes as energy enters and leaves the ocean. Sunlight adds heat near the surface. Evaporation, infrared radiation, and contact with cooler air can remove energy. Currents carry heat horizontally from one region to another, while vertical mixing redistributes it through the water column. These processes operate continuously, so the stored thermal energy of the Gulf is always changing. Seasonal warming generally increases heat content during spring and summer, as the upper ocean absorbs solar energy over many weeks. Warmth can penetrate deeper through mixing and circulation. Later in the year, cooling from the atmosphere and stronger weather systems can reduce this reservoir. The timing and magnitude of these changes vary from year to year. Long-term ocean warming raises the background level on which this seasonal cycle occurs. Observations indicate that the global ocean has accumulated substantial additional heat over recent decades. Regional changes in the Gulf do not exactly follow the global average every year, but the broader warming trend increases the likelihood that periods of high heat content will occur within an already warmer ocean. Heat content is sometimes discussed using a reference temperature chosen for a specific scientific purpose. Researchers can calculate how much warm water exists above that threshold and how deeply it extends. Different studies may use different definitions, so comparisons require consistent methods and data. The value of the measurement lies in its ability to represent depth. Surface temperature can change quickly after a cloudy day or a period of strong wind. A deep reservoir of warm water is less easily removed. Wind may cool the immediate surface while mixing some of the deeper heat upward, leaving the broader upper ocean relatively warm. For this reason, scientists monitor both surface temperatures and subsurface heat. A record at the surface describes one part of the thermal state. Elevated ocean heat content indicates that the unusual warmth occupies a larger volume and may persist despite short-term atmospheric changes. The distribution remains uneven across the basin. Warm currents, eddies, shallow shelves, and regions of stronger mixing each produce different profiles. Maps of ocean heat content therefore show broad patterns rather than a single value for the entire Gulf. Some areas may contain deep warm layers while others have cooler water much closer to the surface. Measurement uncertainty also remains important. The ocean is vast, and instruments cannot sample every location continuously. Satellites provide broad surface coverage, but require subsurface observations and models to estimate heat below. Researchers combine many sources of information to reduce these gaps and to distinguish real changes from incomplete sampling. Within the Gulf Ocean, heat content represents the accumulated result of months of heating circulation, mixing and exchange with the atmosphere. It describes not simply how hot the sea appears at its surface, but how much thermal energy is stored through the upper water column. When that reservoir becomes unusually large, the Gulf is holding warmth in a form that can remain present through changing weather and shifting surface conditions. At the boundary between the Gulf of Mexico and the atmosphere, heat begins to move from the ocean into the air. This exchange occurs across a surface that is only a few molecules thick, yet it connects the large thermal reservoir of the sea with the weather above it. The rate of transfer depends on water temperature, air temperature, humidity, wind speed, and the difference between conditions on either side of the surface. Evaporation is one of the most important pathways. Individual water molecules escape from the liquid surface and enter the atmosphere as water vapor. This change of state requires energy. The energy is taken from the ocean, so evaporation cools the water, even while it adds moisture to the air. Warm water can support faster evaporation because more molecules near the surface have enough energy to leave the liquid state. The actual rate still depends strongly on the air above. If the air is already very humid, it contains large amounts of water vapor, reducing the difference between the sea surface and the atmosphere. Under drier conditions, that difference is larger and evaporation can proceed more efficiently. Wind also changes the exchange. Near a calm surface, a thin layer of humid air can form directly above the water. This layer slows further evaporation because it reduces the moisture difference between the ocean and the nearby atmosphere. Wind continually removes some of this humid air and replaces it with air from elsewhere. As wind speed increases, evaporation can therefore increase substantially. Energy carried by evaporated water is known as latent heat. The heat is not immediately expressed as a simple increase in air temperature. Instead, it is stored in the water vapor and can be released later when that vapor condenses into liquid droplets. This process is central to the way warm tropical oceans transfer energy into the atmosphere. The sea also exchanges sensible heat with the air. Sensible heat refers to direct thermal transfer caused by a temperature difference. When the ocean's surface is warmer than the air above it, energy moves upward and warms the lower atmosphere. When the air is warmer than the water, the direction can reverse. Over the Gulf during warm periods, both directions are possible depending on local conditions. Infrared radiation provides another route for energy loss. The warm sea emits long-wave radiation upward. The atmosphere absorbs some of this energy and also emits radiation back toward the surface. Clouds and water vapor influence this exchange because both interact strongly with infrared radiation. The net result depends on the temperature and moisture structure of the atmosphere. These processes operate simultaneously. Sunlight may add energy during the day, while evaporation, sensible heat transfer, and infrared radiation remove energy. The balance can change within hours. A clear, calm afternoon may favor strong solar heating, while a windy night can increase evaporative cooling and turbulent transfer. Warm Gulf water also contributes large quantities of moisture to the lower atmosphere over time. Water vapor is lighter than dry air when compared at the same temperature, and pressure and moist air can become buoyant when heated near the surface. Rising air expands and cools. If it cools enough water, vapor condenses into cloud droplets, releasing some of the latent heat previously taken from the ocean. Scientists estimate these exchanges using observations from buoy ships, satellites, aircraft, and weather models. Measurements of wind humidity, air temperature, sea temperature, and radiation are combined to calculate how much energy is moving through the surface. Each estimate contains uncertainty because the ocean's surface is constantly changing and because conditions can vary over short distances. The exchange becomes stronger when warm water, humid air, and increasing winds occur together. However, warmer water alone does not determine the atmospheric response. Stability, moisture through different heights, surrounding pressure patterns, and wind structure all influence whether rising air develops into organized convection. Across the Gulf, the surface therefore acts as an active thermal boundary rather than a passive dividing line. Heat stored in the water can leave through evaporation, direct warming, and radiation. Moisture can enter the atmosphere and later release energy during condensation. The continuous movement of energy across this boundary connects the thermal state of the Gulf with the behavior of the tropical atmosphere immediately above it. A tropical cyclone is an organized rotating storm that develops over warm ocean water when atmospheric conditions allow thunderstorms to persist around a low-pressure center. The Gulf of Mexico can provide an important energy source for these systems because its surface is warm, and its upper ocean often contains substantial heat during hurricane season. The exchange begins at the sea surface. Warm water transfers moisture into the lower atmosphere through evaporation. It also transfers sensible heat when the ocean is warmer than the air above it. The rising air carries water vapor upward where cooling causes condensation. During condensation, latent heat is released into the surrounding atmosphere. This added energy helps maintain buoyant rising motion within deep clouds. The process depends on more than warm water alone. A tropical cyclone requires organized atmospheric circulation, abundant moisture, sufficiently weak, disruptive winds at different heights, and a pre-existing disturbance capable of concentrating thunderstorms. Sea surface temperature establishes part of the thermodynamic environment, but it does not guarantee that a storm will form or strengthen. Once a cyclone becomes organized, its winds increase the rate of exchange between ocean and atmosphere. Stronger winds roughen the sea surface, producing waves, spray, and turbulent mixing. Evaporation becomes more efficient as moist air near the surface is continually replaced. The storm can therefore draw energy from a much larger area of ocean than the calm atmosphere above the same water. At the same time, the cyclone changes the ocean that supports it. Strong winds stir the upper layers and can bring cooler water upward from below. This process is known as entrainment. The storm also pushes surface water away from some areas, allowing deeper water to rise. Together, mixing and upwelling can produce a cooler trail behind the cyclone. The amount of cooling depends strongly on the vertical temperature structure. If warm water forms only a shallow surface layer, vigorous mixing can quickly expose colder water and reduce sea surface temperature. If warm water extends much deeper, mixing may still occur without producing the same degree of cooling because the water brought upward is also relatively warm. Storm speed matters as well. A fast-moving cyclone spends less time over one location, limiting the duration of wind-driven mixing. A slow-moving storm can remain over the same water longer, giving its winds more time to disturb the upper ocean. The resulting cooling pattern varies with storm size, intensity, motion currents, and the depth of warm water. The ocean response is not uniform around the storm. Winds are stronger in some parts of the circulation than in others, and Earth's rotation influences the direction in which surface water is displaced. As a result, the strongest cooling can occur away from the storm's exact track. Local currents and eddies further modify this pattern. Scientists observe these exchanges with satellites, buoys, autonomous floats, aircraft-deployed instruments, and ocean models. Measurements taken before and after a cyclone reveal changes in temperature through the water column. They also show how quickly surface conditions recover after the storm passes. Some of the energy transferred from the ocean contributes to the storm's circulation, but much of the heat and moisture moves through complex pathways within clouds and rainfall. Friction also removes kinetic energy from the wind near the surface. A tropical cyclone, therefore, exists through a continuous balance between energy gained from warm water and energy lost through radiation, rainfall processes, turbulence, and surface drag. The relationship between Gulf heat and cyclone behavior is consequently dynamic. The storm draws energy from the sea, while simultaneously cooling and mixing the water beneath it. When the upper ocean contains a deep reservoir of warm water, that cooling effect can be reduced because the mixed water remains warm. When cooler water lies close to the surface, the storm can weaken its own oceanic energy supply more rapidly. Across the Gulf, this exchange links atmospheric circulation directly with the thermal structure of the sea. The ocean supplies heat and moisture, while the cyclone reshapes the ocean's surface and upper layers through wind waves and mixing. The interaction continues as long as the storm remains over water, and the surrounding atmosphere supports its organized circulation. Rapid intensification describes a period when a tropical cyclone strengthens quickly over a short time. Meteorologists often define it using a large increase in maximum sustained wind speed within about 1 day. Thresholds vary among studies, but the idea remains the same. The storm is gaining organized energy faster than usual. Warm ocean water can support this process by supplying heat and moisture to the lower atmosphere. When the upper ocean is unusually warm to substantial depth, the storm may continue drawing energy even as its winds stir the sea. This matters because strong winds normally mix cooler water upward, which can reduce the surface temperature and weaken the energy transfer from ocean to atmosphere. A deep warm layer limits that cooling effect if the water beneath the surface is also warm. Turbulent mixing may bring up water that is only slightly cooler. The storm therefore encounters less reduction in the temperature of the sea beneath it. High ocean heat content can create this type of environment, especially within warm currents and eddies. The atmosphere must also be favorable. Vertical wind shear, which is the change in wind speed or direction with height, can disrupt the storm's internal structure. Strong shear can tilt the circulation and separate thunderstorms from the low-level center. Weak or moderate shear is generally more supportive because it allows rising air and rotating thunderstorms to remain better aligned. Moisture through the middle atmosphere is another factor. Dry air entering the circulation can promote evaporation within clouds and reduce persistent, deep convection. A humid surrounding environment makes it easier for thunderstorms to continue near the center. Moisture is uneven, so a storm can move between more and less favorable regions. The cyclone's own internal structure also matters. A well-defined inner core can concentrate rising motion and organize the release of latent heat. Changes in the eye wall rain bands and pressure field can influence how efficiently the storm converts available heat into stronger winds. These internal processes are complex and can change quickly. Rapid intensification, therefore, cannot be predicted from sea surface temperature alone. Extremely warm water may be present, while strong wind shear prevents major strengthening. A storm may also pass over deep, warm water but fail to organize because its circulation is poorly structured. Conversely, when several favorable conditions occur together, intensification can proceed quickly. Storm motion influences the ocean beneath it. A slow-moving cyclone spends more time stirring the same region, which can enhance cooling. A faster storm may cross warm water before strong mixing can substantially reduce surface temperature. However, motion interacts with storm size, wind strength, ocean depth currents, and the existing temperature profile, so no single speed determines the outcome. Forecasters combine many measurements to estimate the probability of rapid strengthening. Satellites reveal cloud structure, rainfall patterns, and surface temperatures. Aircraft can measure winds pressure, humidity, and the internal organization of a storm. Ocean floats, buoys, and expendable instruments provide temperature profiles beneath the surface. Numerical models combine these observations with equations describing atmospheric and oceanic motion. Forecasting has improved as observations and models have become more detailed, but rapid intensification remains difficult to predict precisely. Small errors in the estimated storm structure, moisture-filled wind shear, or ocean temperature can alter the modeled rate of strengthening. Observations indicate that warmer oceans can provide more favorable thermodynamic conditions, while the development of any individual cyclone still depends on many interacting factors. In the Gulf of Mexico, unusually high heat content is therefore treated as one component of risk rather than as a direct forecast of hurricane intensity. Deep warm water can reduce the cooling caused by a passing cyclone and maintain a supply of heat and moisture near the surface. When the atmosphere and the storm's internal structure are also favorable, that reservoir can support faster strengthening. The scientific concern is based on this combination. Ocean warmth does not create rapid intensification by itself, but it can remove one important limitation on storm development. In regions where warm water extends deeply, the ocean may remain energetically supportive even under strong wind-driven mixing. Rapid change then depends on how effectively the cyclone's circulation can use that energy within the atmospheric environment surrounding it. Forecasting hurricane behavior in the Gulf of Mexico requires a combination of observations, physical understanding, and numerical models. Scientists monitor the atmosphere and ocean continuously because conditions can change rapidly across relatively small distances. No single instrument provides a complete picture, so forecasting depends on many measurements being combined into one evolving view of the environment. Satellites provide the broadest coverage. They observe cloud structure, rainfall, sea surface temperature, atmospheric moisture, and the height of the ocean surface. Different satellite instruments measure different properties, and some can continue collecting useful data, even when thick clouds hide the sea from visible or infrared sensors. These observations allow forecasters to follow large weather systems and identify regions where ocean warmth is concentrated. Buoys add direct measurements from the sea surface. They record water temperature, air temperature, pressure, wind and wave conditions. Because they remain in fixed locations, they provide detailed time series showing how the environment changes as a storm approaches and passes. Drifting instruments and autonomous floats extend this information into areas where permanent stations are sparse. Aircraft become especially important when a tropical cyclone is organized enough to investigate directly. Research and reconnaissance flights measure winds pressure, temperature, and humidity inside and around the storm. Instruments released from aircraft descend through the atmosphere and report conditions at different heights. Other probes can be deployed into the ocean to measure temperature beneath the surface. These observations are fed into numerical prediction models. A numerical model represents the atmosphere and ocean as three-dimensional grids and calculates how temperature, pressure, moisture, winds, currents, and other properties evolve with time. The equations are based on established physical laws, but the real atmosphere and ocean contain features smaller and more complicated than any model can represent perfectly. Forecast uncertainty begins with the initial state. Even a dense observing network cannot measure every point in the Gulf and surrounding atmosphere. Small gaps or errors in temperature, wind moisture, or pressure can grow as a forecast extends forward. Tropical cyclones are sensitive to these differences because their development depends on interacting processes across many scales. Model resolution also matters. Fine grids can represent smaller features, but they require greater computing power. Processes such as cloud formation, turbulence, ocean mixing, and the transfer of heat across the sea surface may still need simplified mathematical descriptions. Improvements in these representations have increased forecast skill, but no model can reproduce every detail. Forecasters, therefore, use ensembles, which are groups of model simulations started with slightly different conditions or model assumptions. When many simulations produce similar outcomes, confidence can increase. When the solutions spread widely, uncertainty is larger. Ensemble forecasting does not remove uncertainty. It makes the range of plausible outcomes more visible. Track and intensity forecasts have different challenges. The path of a storm is strongly influenced by large-scale atmospheric currents, which modern models often represent relatively well several days in advance. Intensity depends more heavily on small-scale storm structure, ocean conditions beneath the cyclone, vertical wind shear, dry air, and internal changes within the core. These factors can make changes in strength more difficult to anticipate precisely. The Gulf adds additional complexity because warm currents and eddies move through the basin. A forecast storm track shifted by a modest distance can place the cyclone over a different ocean heat reservoir. Subsurface observations are therefore valuable, especially when surface temperatures appear uniformly warm while deeper conditions vary substantially. Scientists continue improving forecasts by increasing ocean observations, refining satellite instruments, expanding aircraft measurements, and developing models that couple the atmosphere and ocean more directly. Coupled models allow the simulated storm to cool and mix the ocean while the changing ocean feeds back on the simulated atmosphere. Continuous updates matter as a storm approaches land, because new measurements can narrow uncertainties while revealing changes that earlier forecasts missed. Even with these advances, a forecast remains an estimate rather than a certainty. Extreme Gulf heat can indicate that one environmental ingredient is unusually favorable, but it cannot determine where a storm will form, whether it will strengthen, or how intense it will become. The most reliable assessment comes from combining ocean heat with atmospheric structure, storm organization, and repeated observations as conditions evolve. The extreme warmth observed in the Gulf of Mexico exists within a climate system that is steadily accumulating heat. Human activities have increased the concentration of greenhouse gases in the atmosphere, especially carbon dioxide from fossil fuel use industry and land use change. These gases reduce the rate at which Earth loses heat to space, creating a persistent energy imbalance that warms the atmosphere, land, ice, and oceans. The oceans absorb most of the additional heat produced by this imbalance. Because water can store large amounts of energy, ocean warming develops over long periods and extends far below the surface. Global measurements show that ocean heat content has risen substantially during recent decades, providing one of the clearest indicators of continued planetary warming. The Gulf of Mexico responds to this global trend while also being shaped by regional conditions. Its temperatures vary with currents, winds, clouds, rainfall, river discharge, and exchanges with the Caribbean and Atlantic. Natural climate variability can make some years unusually warm and others less extreme. These variations remain important, but they occur around a background temperature that is now higher than it was in earlier decades. This changing baseline affects the probability of extreme heat. When normal seasonal warming begins from a warmer starting point, temperatures that were once rare become easier to reach. Marine heat waves can become more frequent, last longer, or reach greater intensity. The exact pattern differs among regions and years, but the broader direction of increasing ocean heat is well established. Scientists use long observational records and climate models to separate long-term trends from short-term variability. Models reproduce the basic warming response expected from increased greenhouse gases and show that continued emissions lead to further ocean warming. The precise amount of future Gulf warming depends partly on future greenhouse gas emissions and partly on regional circulation changes that remain more difficult to project. Hurricane behavior responds to this changing environment in several ways. Warmer ocean surfaces can increase the amount of heat and moisture available to tropical cyclones when other atmospheric conditions are favorable. A warmer atmosphere can also contain more water vapor, providing additional moisture for heavy rainfall. These physical relationships are well understood, although individual storms remain strongly affected by wind shear, dry air, internal structure movement, and local ocean conditions. Research indicates that the strongest tropical cyclones are expected to become more intense on average in a warmer climate, while rainfall rates associated with tropical cyclones are also expected to increase. The total number of storms globally is more uncertain and may not increase in the same way. Regional changes are especially difficult to determine because hurricane formation depends on several competing atmospheric influences. Rapid intensification is another area of active research. Observations and modeling indicate that environments capable of supporting rapid strengthening may become more favorable as oceans warm. Some studies also find evidence of increasing rapid intensification in parts of the tropical ocean. However, trends vary by region and data set, and scientists continue examining how much of the observed change results from long-term warming, natural variability, and improvements in storm observations. The Gulf carries additional importance because many tropical cyclones crossing it are already close to populated coastlines. A storm that strengthens quickly over deep warm water may leave less time between major intensity changes and landfall. This does not mean that every warm Gulf will produce a severe hurricane. It means that unusually high ocean heat can increase the potential energy available to storms that encounter favorable atmospheric conditions. Future Gulf temperatures will continue to fluctuate from year to year. Cool periods will still occur, and individual seasons will continue to be shaped by weather and circulation. Long-term warming does not replace natural variability. It shifts the entire range within which that variability operates. The record warmth that draws scientific attention is therefore part of a larger physical pattern. The Gulf remains a dynamic sea governed by sunlight, currents, atmosphere, and seasonal change, but each of these processes now operates within a warmer climate. Observations indicate that additional warming will continue while greenhouse gas concentrations remain elevated, leaving the Gulf with an increasingly large reservoir of stored heat and a changing environmental background for future hurricane seasons. The Gulf of Mexico settles into its familiar seasonal rhythm beneath a changing climate. Sunlight continues to cross the atmosphere and enter the water. Winds continue to stir the surface. Currents continue to carry warm tropical water through the basin, while rain clouds and passing weather systems alter the balance from one day to the next. None of these processes is new, yet the background in which they occur is warmer than it was in earlier decades. Across the basin, heat exists in layers. Some remains near the surface where satellites can observe it directly. Some extends deeper, held within the mixed layer, the loop current, and warm eddies. This stored energy changes slowly shaped by circulation and by the steady exchange between ocean and atmosphere. When tropical cyclones enter the Gulf, they encounter this complex structure rather than a simple sheet of warm water. Scientists continue to measure that structure with instruments above, on, and beneath the sea. Each observation adds detail to a system that is always moving. Forecasts improve as measurements become more complete and models represent the ocean and atmosphere more closely. Uncertainty remains, especially for the exact intensity of individual storms, but the physical relationship between a warmer ocean and greater available heat is well established. The Gulf therefore remains both familiar and altered. Its tides rise and fall, its currents turn, and its summer waters warm, as they have for generations. At the same time, long-term ocean warming raises the baseline beneath those natural cycles. The result is a basin capable of reaching temperatures and heat contents that once occurred less often. Quietly, beneath changing skies, the Gulf continues to store, release, and redistribute the energy that shapes its waters and the atmosphere above.